Thank you very much. So I continue my series of lectures. So yesterday we have discussing about transformation groups, and in particular given criterion for proper actions. And the definition of proper actions is very easy, but actually we have seen that this property is quite delicate. And seemingly it's proper actions like free actions and every orbit is closed. But still, sometimes in the group setting that the action is not proper. And this is a global property and some delicate properties. But we have given at least when the transformation group is reductive, and then for arbitrary subgroups, we have given a necessary and sufficient conditions. And then today, we utilize these criterions and even strengthen these criterions by a kind of quantifications, and then discuss rigidities and deformations, not in the classical setting, but in the more general setting, in a non-Riemannian setting. And tomorrow, not tomorrow, but on Monday, in the opposite directions, that we relax these conditions, and this connects with unity representation theory and like High-Sanders tempered representations. Okay, so let me still begin in elementary fashions. So we are discussing how local geometric structures affect the global nature of the manifold. And the typical examples of the local geometric structure is like curvatures and or also locally homogeneous structures in a more general way. And now let us consider curvatures. This is defined infinitesimally, so it's a local properties. Suppose that M is a pseudo-Riemannian manifold, not necessarily positive definite, but signature is PQ, P positive and Q minus in a P plus Q dimensional manifold. And for simplicity, we assume that it is geodesically complete, namely geodesics are defined all time intervals. And then such a manifold is called space form if the sectional curvature is defined similarly for pseudo-Riemannian manifolds. And if this sectional curvature is constant, we say this is a space form. And there's a small remark that if we change the signatures of metric Z into minus Z, then the signatures PQ switches to QP, and the curvature becomes minus. So there's such a symmetry. And typical example of space form is the following. In the case Q equals 0, this is a Riemannian setting. And then we have three types of model space for space forms. The first case is constant curvature, positive curvatures. So this is a sphere geometry. And second one is curvature 0. This is a flat case, like Euclidean space. And then third one is negatively curved space. This is a hyperbolic geometry. Next, we may consider Lorentzian manifold. Then physicists gave names for such a manifold. An analog of sphere in the Lorentz manifold is called the zeta space. This we also saw yesterday. And then the flat case is called Minkowski space. And an analog of hyperbolic space, namely constant negative curvature space, is called anti-zeta space. And in the group language, we may the model space is written like this way. Okay. Now we also look at an two-dimensional case. Then also there exists a compact model of such forms in the Riemannian setting, namely, in the positive curvature case, two sphere is already compact, and for flat case, if we take a quotient of R2 by Z2, then we have a torus, and this is we end up with a flat Riemannian metric. And also, for hyperbolic space that, as we saw yesterday, that compact Riemann surface, whose genus is at least 2, carries some hyperbolic structures, namely constant negatively curved space. So in each case, we have a compact model in the Riemannian case. And this feature is true not only two-dimensional case, but for arbitrary dimensions in the Riemannian setting. And for example, in the hyperbolic case, there's a general construction by using arithmetic subgroups, but also there is constructions for non-arithmetic lattice as well. Okay, but now let us look at the Lorentzian manifold. Then still in the flat case, we can construct a compact torus endowed with flat metric, just taking quotient of the Minkov space by Z2. Then we have a compact torus. But on the other hand, there does not exist a compact manifold carrying a Lorentzian metric and constant curvatures. This is a special case of the Calabi-Marx phenomenon that we saw yesterday. And but in this case, also there's another completely different proof for the non-existence of two-dimensional compact manifold with, for example, positive curvatures or negative curvatures. So this is to use some characteristic classes, or in this case, one can use Euler class. Suppose that there existed compact manifold with Lorentzian metric. Then at each point taking the directions of positive cones, we would have a non-vanishing vector field. And then by the Poincare theorem that the Euler class must be 0 if it is compact. But on the other hand, Gauss-Bonnet theorem also holds, extends to the pseudo-Riemannian manifold. So in particular, if the curvature is positive, then Euler class must be non-zero if the manifold is compact, and this is a contradiction. So some topological obstructions give some existence of compact model for Lorentzian case. Okay, so this is a typical examples about the study from local to global. So local assumption in our particular example is curvatures and also signatures of the metric. So if we are given signature PQ and then curvature either positive or negative or possibly 0, then we may ask that what kind of the fundamental groups is allowed. And also, if there exists a compact model, namely, if there exists a compact manifold equipped with this local structure or not. So this is a global properties. And we have a quite good understanding in the Riemannian setting, but for the general signature case, this is still already a very difficult question. And even such a, at the first glance, this looks very simple questions, but actually that even this case, this is a long-standing open questions. For example, in the case, flat case, curvature equals 0. So this is connected with the Auslander conjecture. And in the case, curvature is negative that we are going to explain. And partly this is solved, but partly still this is not. So for some of the signatures, it is solved, but for some other signatures, still this is an open question. There's some conjecture, but not solved completely. Okay. So now let us reinterpret these questions by means of the group theories. And first, as we saw yesterday, that for the two-dimensional case, we know uniformization theorem that any compact Riemann surface whose genus is at least 2, then its universal covering is upper half plane, and we may have such expressions. And similarly, for this case, any complete pseudo-Riemannian manifold with signature QP, general signatures, and with say constant negative curvatures. And for simplicity, we exclude the case p equal 1. And for p equal 1, that we need to take a universal coupling. And so just for simplicity, we exclude p equal 1 case. Then any such manifold can be given as the quotient of the model space divided by discontinuous group gamma. Here we recall the terminology discontinuous group from yesterday, that we say gamma is a discontinuous group for geometry if gamma is a discrete subgroup of the Lie group that keeps the geometric structures of X, and moreover, we also assume the gamma action to be proper. And this latter conditions is serious. This is what we learned from various examples yesterday. Okay, so this shows that this is a model space which is responsible for the curvature and signature local property. And the gamma is responsible for global property. And so we are now asking what kind of gamma is possible, like when there exists infinite discontinuous group, or if there exists gamma which is isomorphic to the surface group for higher dimensional case, or if there exists cocompact gamma or covolume finite gamma. So this is a question. And here is a summary of the development over about 60 years. And so still the problem is not completely solved, but this is a state of the art right now. So we explain in terms of the discontinuous groups. So suppose that the G mod H is this homogeneous space OP plus 1Q over OPQ. So this is a pseudo-Riemannian manifold of signature QP with negative curvatures. Then this homogeneous space admits an infinite discontinuous group if and only if P is strictly smaller than Q. So the case Q equal 1 case is what Calabi-Marcus discovered. And yesterday we have explained that Calabi-Marcus phenomenon for the zeta space is generalized for arbitrary homogeneous space for reductive groups, pair of reductive groups G and H. So for any G mod H by means of the real rank conditions. And if we apply that criterion in this case, then this is exactly this condition. Okay, so this is necessary and sufficient conditions. The second one is that some obstructions of compact model. We have seen that for two-dimensional case, that there's no compact Lorentzian manifold with negative constant curvatures. And for two-dimensional case, we have two proofs. One is by using Marcus ideas, and the other is to use Euler characteristics. And for more higher dimensional case, that this parity, so similar ideas of characteristic classes gives some parity conditions. And currently, it is now known that if Q equals 0, or so if this Z mod H admits a cocompact discontinuous group, then either Q equals 0, or of course P must be smaller than Q by the first conditions, and also Q must be even. So some parity conditions arise. Okay, and this is generalizations of this characters classes. And conversely, if P and Q is in the following list, then actually there exists a compact manifold having these local geometric properties. And the first two case is Riemannian case, namely, if Q equals 0, then this is a sphere. And so already it is compact. And if P equals 0, by switching the signatures, this means that it's sorry, I think I said the opposite way, that if P equals 0, this is a sphere. And if Q equals 0, by switching the signatures, this is a hyperbolic space. And then hyperbolic manifold admits some cocompact discontinuous groups. So the first two is Riemannian case. And then we have another cases, and this is a pseudo-Riemannian manifold. And the P equal 1 case corresponds to the anti-Dogita manifold. And so for anti-Dogita manifold, it carries a compact model if and only if the dimension is odd. So namely, 2n plus 1 is odd. So this is, in this case, this is necessary and sufficient. And then for P equals 3 case, this is not a Lorentz manifold, but more general pseudo-Riemannian manifold. But if Q is a multiple of 4, then we have a compact manifold with the same geometric structures. And then there's one more example that there's a 15-dimensional manifold that signature is 8, 7, and then having negative constant curvatures. So this is that was proved so far. And I guess that this is a complete list of having cocompact discontinuous groups, but it is still a conjecture statement. Okay, so what we want to do is to develop a method, not only working on these particular examples. And so particularly that we want to analyze pair of real reductive groups, and then consider homogeneous space Z mod H. Then always this carries some pseudo-Riemannian structure on which G acts. So we have there's a huge isometry group, namely G acts as isometry groups. So in such situations that we want to know in which cases there's a lot of discontinuous group. So in what cases there is such a homogeneous space admits a large discontinuous group. Large means that not a finite group, but infinite group. But even better is that like a cocompact discontinuous group or covolume finite discontinuous group. So what is the local structures that allows such a global picture? This is a questions. And today I'd like to explain 3 topics. One is that the obstructions of having cocompact quotients. So one obstructions already we have seen that the Calabi-Marx phenomena in the first lectures. And also character classes, by using the character classes, we have some topological obstructions. That I have explained some simplest ideas in the case of the two-dimensional case, but I don't enter in detail for this topological obstructions by using characteristic classes and its generalizations, but certainly gives certain conditions. But today, I'd like to explain one more obstructions coming from cohomological dimensions. And then on Monday, we also give some obstructions coming from unity representation theory by using the idea of the Margulis. And this is connected with particularly matrix decay asymptotic behavior of matrix coefficient of unity representation and the branching problem. So this is for the Monday lectures. And then also I want to discuss, so this is some negative result that this gives obstructions for the existence. So this means that the conclusion is that there's no compact manifold. But also we want to find some positive results, namely for some sufficient conditions that allows a compact manifold endowed with such a local geometric structures. So we also explain some constructions of compact quotients that we name standard constructions. And then, so this is the constructions, but then we may wonder if such a constructions, we may deform it or not. If it is not able to deform it, then usually such a structure is called the rigidity theorem. And if one can deform, and then this opens new directions of higher deformations, higher dimensional deformations. So this is what I want to briefly explain some typical examples and method of the proof. Okay, so let us start about again very elementary examples. Consider vector space Rn, and then let abelian discrete group Zk act on Rn. You may think about just the translations, or you may think about affine actions, whatever. Then the following property, I think, is easy to prove. So if this acts properly discontinuously on Rn, then K cannot be bigger than n. For example, Zn plus 1 cannot act properly discontinuously on Rn. And moreover, if this acts properly discontinuously, then the quotient space of Rn by Zk is compact if and only if K equals n. I think everyone can believe this. Then question is that what is K in here, and what is n in here? So we want to consider non-commutative actions of discrete groups on some manifold, not necessarily vector space. Then what is K and what is n? And then what is this inequality? Okay. So first, let us consider what is K here. So this is in blue. So we use cohomological dimensions for discrete group. So for an abstract group gamma, we define cohomological dimensions denoted by CD gamma. But for simplicity, we consider over Z, but over R. And then this is the projective dimensions of R as a trivial R gamma modules, or equivalent that we consider cohomology of gamma, group gamma, with coefficient on gamma module A R gamma modulo A, and then consider supremum of N for which the cohomology doesn't vanish. Then cohomological dimension of zk equal k. So this is our interpretation what is k for zk. And for the surface groups, that the cohomological dimension equal to. So this is our understanding of k for zk. Then next, I want to understand what is n for Rn. We are particularly interested in the homogeneous space of reductive groups. So suppose G is a real reductive group and K is maximal compact subgroup. And then we want to say that kind of non-compact dimensions of the group G is probably dimension G minus dimension of the maximal compact group K. So we call this as a non-compact dimensions of the group Z, denoted by dg. Okay. Then now we want to discuss about homogeneous space G mod H. Then the non-compact dimension of the homogeneous space dg, G mod H would be dg minus dh. So probably that we have some such an additive structures of non-compact dimensions. And actually, this is the right definitions. So suppose H is an reductive subgroup of Z. Actually, we can drop the assumptions of reductiveness. Just connected to closed subgroup will work. But we are interested in this lectures when H is reductive. Okay. Then suppose that gamma is a discontinuous group acting G mod H. So namely, gamma acts properly discontinuously on G mod H. Then we have, so similar to the abelian case, that we have the following inequality, namely, cohomological dimensions of the discrete group cannot be larger than the non-compact dimensions of the homogeneous space, namely dg minus dh. And moreover, this inequality becomes an equality if and only if gamma is cocompact, namely double coset space is compact. The idea of the proof is to use cell spectral sequence that we compare two topologies that we start from G mod H, and then this G mod H is homotopic to some compact submanifold in here. And this compact submanifold, as a notation shows that this K is maximal compact subgroup, and the intersections is also maximal compact subgroup of H. We choose K in this way. Then G mod H is homotopic to this one. And the difference of the dimensions is exactly what we call non-compact dimension. Then on the other hand, if gamma acts properly discontinuously and freely, then we have a covering to the quotient space. Then we compare topology of two spaces. And then this topology can be compared by using cell spectral sequence, and then E2 terms appears some cohomology of gamma and so on. So this is idea of the cells. So we have such a numerical criterions for cocompactness. So this is a number. So this is a numerical criterion for cocompactness under the assumption that the action is properly discontinuous. Okay, and similarly, so this is a discrete group setting, but also we may have an analogous theorem for continuous setting, namely, suppose that connected group L acts properly on Z mod H, then also we have a similar inequality. And in this case, that we just use non-compact dimensions of connected group L. And then if the action is proper, then the non-compact dimension of the subgroup cannot exceed the non-compact dimensions of the geometry. And the equality holds if and only if double coset space is compact. Okay, so this is again the numerical criterion for compactness under the assumptions of proper actions. So now what we have obtained is the following. So our notation is that gamma or L is the subgroup of Z, and I use L upside down of gamma to denote connected group usually. And H is usually we assume reductive homogeneous reductive subgroups. So very often we can drop the reductive assumptions. In this talk, I assume H is also reductive subgroup. Then we have now understand quite well about the criterions of proper actions of L or gamma. So this was a main topic theorem in the first lectures, properness criterions. And then today we have seen that under the assumptions that the action is proper or proper discontinuous, then we can check numerically by numbers if the action is cocompact or not. So this is what we have reached so far. And then by using this as a tool, we have some obstructions and constructions of compact quotient. So the first one is obstructions, cohomological obstructions for the existence of cocompact lattice, cocompact discontinuous group. So this figure is what we have seen yesterday, that we expand H by multiplications of compact set, first by the right. So this is still kind of a tubular neighborhood, but then from the left, then depending on how non-commutative the group is, the shape of this expansion changes. Okay. Then the obstructions for the some cohomological obstruction for the existence of cocompact discontinuous group is formulated as follows. So this theorem says that the conclusions is that Z mod H does not admit the cocompact discontinuous group. So this is the conclusions. And then what is the assumption? Aside from this given reductive groups H, there exists another subgroup H prime having the following properties. The first condition is that H and H prime is equivalent under this coarse geometry. And the second one is that this is numbers, that the non-compact dimension of H is smaller than non-compact dimension of H prime. Then the conclusion that G mod H does not admit the compact discontinuous group. So the idea is the following, that if there exists such a subgroup, another group H prime, then the non-compact dimensions of the geometry of G mod H that we consider is compared with non-compact dimensions of Z mod H prime. Then Z mod H has larger non-compact dimensions. On the other hand, since H and H prime is equivalent in this coarse geometry, and then properness for acting on Z mod H and acting on Z mod H prime is equivalent. This is what we have seen. And then this gives some contradictions. So this is an idea of the proof. And here's the simplest examples of this theorems. So the conclusions is that SL3C over SL2C cannot admit the cocompact discontinuous groups. So namely, there does not exist compact complex manifold which is obtained as a quotient of SL3C mod SL2C. To prove this, we use this theorem 3 by taking another subgroup H prime to be SU21. Then the non-compact dimension of SU21 is 4, but on the other hand, non-compact dimension of SL2C is 3. So we have the desired inequality. On the other hand, by looking at the maximal split Cartan subalgebras of H and H prime, we can check that H and H prime is equivalent in this coarse geometry. And so we can apply this theorem and we conclude this. So this is a brief idea for cohomological obstructions for the existence of compact discontinuous groups. And actually, that this has a quite wide application. So many homogeneous spaces can be proved that they don't have a compact discontinuous group by this method. Okay, so this is one direction that we have seen. And now, I don't pursue these directions, but now let us talk about positive directions, constructions of compact. So what we have seen that some homogeneous space G mod H does not have a compact model, so namely does not have a cocompact discontinuous groups. But on the other hand, some other homogeneous space like odd dimensional anti-Dogita manifold carries a cocompact discontinuous group, namely carries some there exists a compact manifold whose local structures is given by this homogeneous space G mod H. Then how to construct it? So this is what I'm going to explain now. So our setting is as usual that we consider reductive groups and then reductive subgroup H. And then we want to take a quotient by discrete group gamma so that the double cross space is a compact manifold. This is what we want to get. But just taking a discrete subgroup gamma, then we have seen that the quotient space may not be Hausdorff in the general setting where H is non-compact. Then how to do that? An idea is the following. So if H is non-compact, the group G acts isometrically on G mod H, which carries some pseudo-Riemannian structures, but never acts properly. So the idea is to find some subgroup L which still acts properly, and of course isometrically. So first try to find such a subgroup, and particularly try to find a reductive subgroup L acting properly. And then we regard this L as a safety zone. Namely, take any arbitrary discrete subgroup in this safety zone, then automatically this action is properly discontinuous. So step 2 is take a discrete subgroup gamma inside L. And for simplicity today, I take a torsion-free discrete subgroup gamma. Okay. Then the result is that gamma acts properly discontinuously and freely on X. And we call that such a resulting quotient space, quotient manifold. So now this carries some Hausdorff topology and smooth manifold structures. And this resulting space we call standard quotient of the model H. And then simple corollary of these constructions is the following. If there exists quite large subgroup L in the following sense. So L is a reductive subgroup L acting properly on X and also cocompactly. Then the conclusion is that this geometry, namely X equals Z mod H, admits the compact quotient X mod gamma. So the proof is one proof that by a theory of Borel that there exists compact discrete subgroup gamma in L. For example, one can take an arithmetic lattice in L. And then taking finite index subgroups, we may also assume that gamma is torsion-free. And so such a gamma is cocompact in L, and L is cocompact in X. So gamma is also cocompact in X, and acting properly discontinuously because gamma sits in this safety zone. And the advantage of this theorem is that the assumptions is easily checked. So namely, this assumptions is computable. So properness criterions that we have seen in the first lectures. And in particular, if the subgroups are reductive, then this is particularly easy to compute. And then for the cocompactness, we have just seen that for cocompactness under the assumptions proper actions, we can check numerically cocompact. And here's some examples. For example, we consider 15-dimensional manifolds. And then a statement is the following. There exists compact manifold of dimension 15 that has a pseudo-Riemannian structure of signature 87 and having negatively constant curvature. As we have seen that the model space is given by 088 mod 087. Then the idea is to find an appropriate safety zone, namely reductive subgroup L acting properly on this space. And in this particular example, we take L to be spin 81. And then we consider spin representations. Then spin representations embed into 088 of these signatures. Then by the properness criterion that we have seen yesterday, we can check that L acts properly. And also, non-compact dimensions with L is 8, and non-compact dimension H is 56, and then the summations is 64, which is exactly the non-compact dimension of Z. This shows the cocompactness. So we have obtained compact quotient of 15-dimensional manifold. This is what we have seen in the table, this green part. So this is a particular example of this type. But if we consider, for example, arbitrary reductive symmetric space, then, of course, if this reductive symmetric space is Riemannian, then all of the Riemannian symmetric space admits cocompact discontinuous group. So this is a theorem of Borel. But suppose that this is a non-Riemannian symmetric space. And assume that this is irreducible non-Riemannian symmetric space. Then there are 11 families of irreducible non-Riemannian symmetric space. For example, this we say it is a family. So this is arbitrary even number. And this we count also another family. This is multiple 4. And then there are 11 families of irreducible non-Riemannian symmetric space that admit cocompact discontinuous groups. Namely, there exists a compact manifold modeled on, so there exists compact locally symmetric space of indefinite signatures. And also, there are some sporadic ones like this one. This is some isolated one. So there are finitely many sporadic. And so this is, and in the case G is simple Lie groups, and then very recently that Tojo gave a proof for the exhaustion. Okay, so now we have explained that some obstructions for compact manifold with some local homogeneous structures. But also, we have explained the constructions that we call standard constructions for compact quotient. But now we ask that if such a construction is isolated or not. So this is rigidity or deformation theory. So again that start with the classical examples, classical Riemannian setting. So deformation theory in the typical case is a Teichmüller space of compact Riemann surface that describes variations of complex structures. And if the genius is at least 2, then also this describes variations of the hyperbolic structure. And we need the parameters 6g minus 6 if the genius is at least 2. And we want to, if we try to interpret this as in the group terminologies like SL2R and SO2, then this gives a direction for generalizations. So namely, this model space G mod K is a Riemannian symmetric space. And this directions is still classical result that suppose that G is a simple Lie group and G mod K is irreducible Riemannian symmetric space. Then Selberg-Weiss local rigidity theorem says that interesting Teichmüller space exists only in the previous case, namely only the dimensions is 2. In this case, gamma admits continuous deformation, and otherwise rigidity holds. And what is the meaning of the continuous deformation? I'll give more precise, more rigorous definitions later. Not necessarily Riemannian case, but more general case. But Selberg-Weiss local rigidity says that essentially that interesting Teichmüller space for the classical Riemannian setting is only this compact Riemann surface. But we shall see that in the non-Riemannian case, the features changes completely. So for this, first we need to formulate deformations. So our setting is the following: that X is the geometry and Z preserve some geometric structures. And so like X is a homogeneous space and Z acts on X. And then we also fix abstract discrete subgroup gamma. And then we formulate deformations of the quotient by varying this homomorphism phi. So we fix gamma and Z and X, but we change homomorphism. And then if we change such a homomorphism, then for each homomorphism, we may think of the quotient X mod phi gammas. Then we want to say that this is the deformations of X mod gammas. Then we need to clarify 2 problems. The first one is that if there exists a non-trivial deformations, variation, if it is possible to vary homomorphism or not as a group homomorphism. And second one is that even if we can deform such a homomorphism, then proper discontinuity may be destroyed. And so we need to prove some stability of proper discontinuous actions. Okay, so with this in mind, let us formulate. So the same setting, and first we consider a set of all homomorphisms from gamma to Z. For example, if gamma is finitely generated and finitely presented, then this set is analytic varieties. And on this, we have a natural actions that G acts on as an inner conjugations. And then also the automorphism group of gamma acts on this space on the preimage. Then inside this, we choose interesting homomorphisms for our problem. Namely, this homomorphism U from gamma to Z. First, this is an injective homomorphism. And second, gamma acts on X through U properly discontinuously. So we are interested in such a case. So this is a subset. And this subset is obviously stable under the actions of these two groups. So we take a quotient. And actually, that this inner automorphism is trivial deformations. And so we need to take a quotient by such a trivial deformations. So we take a quotient of inner automorphism denoted by tau T gamma Gx. And this T is Teichmüller space T. So this we call higher Teichmüller space. And then also we take a quotient of auto gamma. And this M is taken from this modular space, M gamma Gx. So this is the definitions. And so we are interested. So if this is isolated, so or if it has a dimension. If it has a dimensions, we say that it has a continuous deformations. But if it is isolated, this is a rigidity. And in the classical case, that if we take G equal SL2R, and X is the upper half plane, and gamma is fundamental group of the surface group, then this is exactly the Teichmüller space of Riemann surface, and this is the modular space of the Riemann surface. But now our notations is also works for arbitrary homogeneous space. Okay, now we ask that if we can deform such a discrete subgroup that we constructed as a standard quotient of X. So namely, we have taken a reductive subgroup L. So this is a safety zone acting properly. And then we take a discrete subgroup like cocompact lattice or finite volume lattice. Then we have a proper discontinuous action. And this is called the standard quotient. So we want to consider its deformations. And inside L, we don't have enough deformations as the Selberg-Bell rigidity says. And so we try to deform outside of this safety zone. Then we have more possibility for deformations. But then problem arises that if we are out of the safety zone, then the action might not be proper discontinuous. So here's some examples. Again, very small, simple example. We consider Z acts on R by translations. And then quotient space is circle. And then small deformations of circle, we expect to be still circles. Like if we slightly change the generators, and then the radius of the circle, diameter of the circle may change, but still the quotient space is circle. And so it seems to that proper discontinuity is preserved. But actually, this is not true. If we consider small deformation inside the affine transformation groups, and then change a little bit, not on this part, but for this coefficient, A to be 1 plus epsilon. Then this action has a fixed point. And so this fixed point is the accumulation point. So the quotient topology of these actions is not Hausdorff. So if this means that if we make a small deformation of the circle, then no more Hausdorff. So this is the nature. So small deformations still are manifold. It's not obvious. But nevertheless, Goldman raised the following conjecture. In the case X equal 3-dimensional anti-de Sitter manifold, in the group language, this anti-de Sitter space is 3-dimensional Lorentzian manifold, but this is just a group manifold SL2R. So this is 3-dimensional manifold, and the Killing form gives such a structure. And we have an action from left and right. So this is the case. And but we also know some counterexample for one-dimensional case. So Goldman's conjecture says in the opposite way. And it turns out that his conjecture is true for this anti-de Sitter space. And the proof uses some criterion proper actions. But now I explain a little bit more general statement that not only a 3-dimensional case, but we compare Selberg's very local rigidity that only 2-dimensional geometry allows an interesting Teichmüller space for the classical Riemannian setting. But on the other hand, if we allow pseudo-Riemannian case, then for arbitrary high-dimensional space, so I take this as a group manifold case, and from left and right action. Then there exists cocompact discontinuous groups, which has a non-trivial continuous deformation. If and only if the group manifold from left and right actions as a homogeneous space, G is locally isomorphic to the Lorentz group or SU2N1. So exactly the case that having the Kazan property T. So trivial representations is not isolated in the unity ideal. And the proof of one directions is to prove infinitesimal rigidity coming from the cohomology. So this is the standard argument. And so non-trivial part is to construct deformations and prove properly discontinuity is preserved under small deformation of the reduced case. So this is actually to strengthen the properness criterion that we have seen yesterday. So yesterday we recall that properness criterion is given in general that take a Cartan projections of the subgroups and then take epsilon neighborhood, and then take a Cartan projections gamma, and then this intersection is at most finite. This is the criterion. But the idea is that to change from this epsilon neighborhood that by some cone, then this gives a stronger condition. So we consider quantifications of properness actions in the following way. So this is the last slide that we call sharpness constant C and C. So this is the quantifications of strong proper actions. So namely, if instead of the epsilon neighborhood, we consider such a cone around the projections of mu h, this is the subspace. And if all the orbit is outside of this cone, we say this is sharp or strongly proper actions. So this outside of the cone is stronger than outside of the epsilon neighborhood. And this angle is the most important part. this small c gives some angles, and this large c gives some distance here. So this is less important. And then the main idea is that with this strongly proper actions, that this constant behaves well under small deformations. So if the starting point satisfies strongly proper actions, then small deformations is still strongly proper actions. So this is a key idea of the proof. So I think this is what I wanted to talk about today. Thank you very much.